Until quite recently, when you got an exception in your Haskell code, at times it could be quite difficult to figure out where exactly the exception was coming from. In most other languages, you get at least an exception backtrace, but not in Haskell, at least not with some manual work. That has all changed in GHG 9.10, and not only do we get exception backtraces, we also get a very powerful mechanism for general exception annotations. It's a feature that I've personally long been waiting for, and so I'm quite happy to talk about it in today's episode of the Unfolder.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Right. So I want to start with a more general mechanism of exceptions, except annotations, and only then talk about backtraces in the second half. So to motivate it, suppose that we are dealing with a networking library. I happen to have been working on the networking library, so it's on my mind. But
the running example.
Yeah, last couple of episodes, yeah, exactly. And suppose that we have an exception that we throw in this library when you're trying to write to a stream, some sort of networking stream, when the stream is already closed. Right, so we might have a stream closed exception, which maybe carries a stream ID. Maybe that stream ID is just a number for our purposes here. And in order for this to be an exception, it needs to be showable, and it needs to be a member of the exception class. Now, if you haven't seen this before, this class, it's a way to make your own kinds of exceptions. And the most important thing that this does is tell you how to show this exception. There's some other details there, but it doesn't need to, we don't need to worry about that today. So just as a very simple example, we might have an example function that throws this exception. So we might say throw stream closed 1. Right, and now if we run this example, so I'll just example throw, sorry. I have set up a main function that just calls example the example here. So now if I run this program, right, the program is just calling this function, we see that it crashes with an exception, stream closed. Okay. All right. Now, maybe we are debugging this, and maybe we want to know, okay, where's this exception coming from? And maybe we want to know, okay, we have this exception. That means that we were writing to a stream. What were we writing, right? Maybe it would be useful in our debugging efforts to know what we were writing. And so we might try to some sort of annotation, right? So we might introduce a new kind of exception, and it carries the old stream closed exception alongside some additional information. And maybe this information, the string, is just the bits, sorry, the bytes that we were trying to write to the stream. Right, so this also is an exception in its own right. And so we might try to annotate as follows. We might try to run the original code, catch the stream closed exception, right, the one that we're interested in debugging, and then throw a new exception that maybe we're writing high at this point alongside the old exception.
Okay.
So if we run this and we run our code, then we now see the annotated exception being thrown. Now, this is useful, but it has a very important limitation. Suppose that somewhere else, maybe in our own code, or maybe in the library that we're writing, or maybe somewhere else, right, there is some other code that we're not in control of that is also catching the stream closed exception. Right, now, if we now call our annotated function, right, which, remember, is catching the original exception and then rethrowing it as this annotated exception, if this is trying to catch this exception, right, and maybe what this is doing, maybe this is just printing the exception, right? So stream closed, maybe just get some additional information. It doesn't rethrow it. If we now call this and we run our code, we can see it did not catch it, right? This prints it and did not happen. Why? Well, annotated one caught the original exception, threw it as a new exception of a different type. And exception handling in Haskell is type-based. And so when this guy here is trying to catch the original exception, it doesn't manage because the exception that's being thrown is no longer of type stream closed.
Right. And I guess the same argument to some extent applies also to just changing the original stream closed exception, because if we are not in control of this piece of code in catch 1, then we would have to change that as well, right?
Yeah, that's right. I mean, you could, maybe in some cases, you could add some additional information here.
Mm-hmm.
Now, there's two problems with that. One is that you might not know that information at the point where you throw the exception, right?
Mm-hmm.
So in which case that you have to make that information optional or something, right? But indeed, also, if you do change that type, then everywhere else where that exception is being caught, you might not use more problems.
Right.
So, yeah. So, one of the new features of GHC 9.10 is that we can have arbitrary exception annotations. You can attach arbitrary pieces of data to existing exceptions. So what does that look like?
Without having to change the type.
Without having to change the type at all. Yes, exactly. So in our case, we want to know what we are sending, right? This string, this hi. And again, this needs to be, it will be useful if we can show this thing, right?
Mm-hmm.
And now there's a new class in GHC called exception annotation. And so here, for when we define new exceptions, we need an instance of exception. When we define new exception annotations, we need an instance of exception annotation. And again, the most important thing that this does is tell the runtime how to display annotations. Mm-hmm. And by default, it uses show, right? So that's why we also derive show here. Mm-hmm. So let's try to rewrite annotate 1 here in a different way. We are no longer going to catch the original exception. Instead, we're going to use a new function called annotate.io from the base libraries. It's in control.exception with some annotation, right? And in our case, what we're annotating is this sending here, right? And then in the body of this, we call a function. What this will do is any exception being thrown by example throw here will now be annotated with this particular annotation. And so this, by the way, is a third reason to Anders' question, like couldn't we just modify the original exception type? In addition to the two reasons I already mentioned, perhaps there's tons of exceptions being thrown here, or perhaps we're not exactly sure which exception is thrown. This will.
We don't even need to know, right? I mean,
we don't even need to know. Exactly.
Yeah,
we don't even need to know. Yeah. So whatever exception is being thrown here, it's getting annotated. So if we now run this program, annotate2, oops, we see that the exception is being thrown here, and we see the annotation alongside the exception. Right. So when the exception is thrown, not only is the exception itself shown, but also all of its annotations. And if you wanted to, you could also process these annotations in code. I won't be talking about that in the episode, but it's possible. So now let's see what happens if we catch this thing, right? Previously, when we tried to catch the original annotation, sorry, the original exception, it was failing because, right, we were throwing a new kind of exception, a new type rather. With the new approach, that is no longer the case. So we can still catch this exception and then print something. And now if we call this program, we see that it is indeed being caught, right? The exception is caught, and we're running this code here.
A quick question. I think you already said this, but Kriov is asking, where is annotate.io defined?
Yeah, it's in so in GHC 10, this comes from control.exception.
But yeah, it's only, there is a library change in GHC 9.10,
yes.
right?
There's a bunch of, yes, exactly.
Before 9.10, you cannot use this feature.
Correct.
Yeah.
Correct. Yeah. Yeah. All right. So let's think a little bit about what happens when we catch an exception and then rethrow it again. What happens to annotations? Right. So let's look at a simple example first. Maybe we are going to call annotate2. And remember, annotate2 was this program here, right, where we call example throw, which throws a stream closed exception, and then we're annotating that exception using annotate.io with this sending annotation, right? That's what this is doing. Right? And now we catch, but we catch an exception that is not being thrown. I'm using IO exception as an example here. I could have written anything here, anything other than stream closed. Right? So we can say print cod exception, and then we just rethrow it. Rethrow, just throw away, obviously.
Right, and the big question is whether, like, what happens to the annotations that E might have, right?
Yeah, exactly. So if we now run this program, let's call this, let's make sure that we actually call it. We see that, the original exception is thrown with its annotation. But in a way, that's unsurprising, right? Because we're not actually catching it at all, right? We have installed an exception handler for a different type. So let's see what happens if we do catch a stream close exception and then rethrow it. Now, this is a more interesting example. Right, so we run it, and we see we get the print statement, right? That's this guy here. And then the program crashes with the exception because we're throwing it again. And we have lost the annotation.
Right,
the annotation, we're not seeing the sending hi anymore here.
Because it's a new exception, right?
Ish. Yeah, not quite. I mean, we're throwing E here.
Yeah, it's the same value, but...
It's the same value, yeah.
And
the reason that was lost is because, this is a bit of technical detail, but when you throw an exception in Haskell, the actual exception that gets propagated up gets wrapped in some sort of envelope. That envelope is called some exception. And it's actually some exception that is carrying the annotations. And so here we're basically unwrapping that envelope, we're looking inside, but the thing that we're getting from the envelope is only the exception without the annotations. So we can fix this in two ways. One is there is a new combinator called exception with context. So we can say exception with context, like this. And now we can also throw an exception with context. And so now we're very explicitly saying, when I look inside this envelope, don't just give me the exception that's in there, also give me the context. And the context is precisely the annotations. So now when we run this, we see the print statement happening here, called exception, and then the exception with the annotation still there. Right? The annotation is now still present. We have not lost it. And if you wish, you can modify this context. You can remove some stuff, add some stuff. There's functions for.
So it's not opaque. There is.
It's an opaque type, but there's an
interface.
There's an interface for it.
Yeah.
There's an API for working with it. Yeah.
Okay.
Exactly.
Okay.
So this is quite nice, but you do have to remember to do this. So there's the exception backtrace proposal where all this stuff is coming from. It's actually a huge proposal, and it's I think it was accepted or started for 4 years ago. It's been a long time in the making, and the reason it's been that long in the making is because it's been quite complicated to get all the bits and pieces working together. Right? There's a lot of working parts to it. Now the vast bulk of the proposal has been accepted and is now available in 9.10, but there is one part of the proposal that has not yet been accepted. So I've re-implemented this part of the proposal here so I can show you what it is. So the final part of the proposal is that the behavior of catch would change. And I have locally here implemented the proposal as this new function, which I've called catch 202 because it's issue 202 on the proposal. But if I call this catch rather than the original catch, and then look at what happens, I'm seeing first the print statement, right? That's this guy here. And then I'm seeing the exception. And now this is something very interesting. We're seeing the exception here. That's the one that we're throwing. And it has an annotation. Now that annotation comes from the new behavior of catch. The new behavior is if you throw an exception in the context of handling another exception, I will automatically and always add an annotation that says, I was throwing this thing while I was handling this exception, right? And that exception does have the annotation associated with it. So this is something you can definitely implement yourself. I mean, it's like 5 lines of code in this repo here. But of course, you then do need to call the other catch, right? So if this catch lives somewhere else, somewhere in the library code, and you're not really sure where, then you do lose this information. So the proposal is to change the behavior of catch to be the behavior of catch 202, but that proposal has not yet been accepted. There's a link in the video description with all the details there. So if you have an opinion on this, please go to that ticket and chime in. It will be very, very good to get some sort of consensus there. But personally, I find this is very useful. So I would definitely be in favor of this proposal being accepted. But there are some details there to be considered.
It's certainly not taking sides on this at all, but like it looks like it could potentially get a little bit confusing. So I was briefly confused when I saw the message there with the sending hi in the last line, that it is actually an annotation for this exception that is like in this while handling. So like, I mean, could the layout somehow be better?
That is certainly true. Yeah, definitely. I think the pretty printing of these exceptions certainly could have some love. In fact, in the very repo that I have here, I actually have some code. I wouldn't bother showing it now, but there is some code in the repo that you can also link in the video description, where I'm actually showing the actual structure. So you can, like, with indentation and everything, so that makes them much easier to see. So yeah, I agree. This could definitely
but that's probably sort of like a minor thing. I mean, it's presentation. Yeah.
All right. So that's the first half of the proposal, and also the first half of the episode, which is this general framework for annotations. Now, one particular kind of annotation that you want is where did the exception come from, right? Where was it thrown? And so there is a new feature in 9.10 called a new function, which is called collect backtraces. So let me show you what that looks like first. Suppose I have some function that I've called top1, and top1 calls another function, which I'm calling middle. And the middle function calls the bottom function. And the bottom function actually does something interesting. It's going to call this new function, which is also introduced in 9.10, called collect backtraces, which is going to give you back a bunch of backtraces.
Again, from control exception? Or?
It's a slightly lower level. It might be control.exception.backtrace. I think there's a couple of submodules there, and the most important functions are all re-exported from control.exception, but not everything. So it might be that this is a slightly lower level. I'm not 100% sure. Check those. All right. So one of the things that we can do with these backtraces is, in fact, basically the only thing. This is a completely opaque type at the moment, which is somewhat unfortunate, but it's displayed. That's how you can display these backtraces. Now, if I disable my annotation example and add my backtrace example, so we're going to call main calls this backtrace example, and backtrace example now calls top. Right, so main backtrace example.
I think.
Oh, top1. Yes. Thank you. Yeah. All right. Let's run this. And we're seeing this is the backtrace here. And we're seeing that it is basically empty, right? The only call is the call to collect backtraces itself, which is not particularly useful.
And also, just to clarify, because like displayed backtraces always sort of create the association of the program having crashed. I mean, there is no exception in this program at all, right? This is like successfully running to completion. It's just printing the backtrace at that point.
Yeah, exactly. Exactly. Yeah. So you could use this in many ways, and I find it actually rather useful. But let's come back to that point in just a bit. So the backtrace, we get a backtrace, but it's not very useful. And the reason for this is that this is a Haskell stack backtrace, and if you haven't used those before, the critical thing to note is that it requires user annotations on which functions you want to add into the backtrace. So if I want bottom to appear in the backtrace, I must annotate it with this Haskell stack thing. Right? And now if I call this again, I see bottom calling collect backtraces. All right, but still nothing else. So the way that this typically works, either you just annotate a whole bunch of stuff, or you know what you're interested in and you annotate those, or you just do this sort of a bottom-up approach. Okay, where does bottom get called from? Okay, bottom was called at main 92. Main 92 happens to be middle. Oh, okay. Where was middle called from? All right, let's add another one. All right, let's run this again. Middle was called at main 89. What is 89? Oh, that's top. All right, so now let's add one here, right? So and you iterate this process.
Right.
It's a bit laborious, right? It's not great.
And you really need it all the way up, right? If any of these, like if you remove the one from middle, then you'll again only get bottom
Exactly.
and collect backtraces.
That's right. That's right. Yeah, you can't interrupt the chain. Yeah. So this is certainly useful, and I have used this often, but it is laborious. So there is an alternative, which is there's actually multiple kinds of backtraces that we can collect. And by default, the only one that's enabled is the Haskell stack one. The one that is most useful, in addition to the Haskell stack one, is based on cost centers. So there's a new function, again, from control.exception.backtrace, I think, where you can set which backtraces that you want to collect. And the reason that this is all optional and configurable is because collecting these things is expensive at times, right? So Haskell code can be throwing quite a bit of exceptions. So collecting a call stack at every point is potentially expensive. So that's why this is opt-in. Now, if you don't know what cost centers are used to profile Haskell code. So it's like, so much percent, like this percentage of the code is being spent in this function over here, this percentage is spent over there, right? And the over here and over there parts are introduced as cost centers, right? So GHC will annotate your functions, add some additional instrumentation here, here and there to mark where we're assigning costs. And the backtrace proposal piggybacks on these annotations to use these cost centers also for collecting a backtrace. Now, to use this, I do need to enable profiling. So I'm just going to call run here, and I'm telling Kerbal I want to enable profiling, please. And now, oops. Oh, that actually worked. Okay, interesting. All right. So now I'm seeing two backtraces. The Haskell stack one is still there. Right? We can toggle each of them individually on or off. But we also see another one, and this one is very useful, right? It tells us that main called backtrace example, which called top one, which called middle, which called bottom. And we didn't have to annotate main. We didn't have to annotate backtrace example, right? This does not depend on user annotations. It does depend on the exact placement of these cost centers. So that may, in certain cases, be less or more ideal, but this is often very useful.
And if you do it without profiling, then it's just empty, or? Yeah,
that's right. So if I don't enable profiling, then the cost center is just empty. Yeah, exactly.
And if you manually add another cost center? Oh, no, okay.
I don't even know the syntax for that.
SCC pragma, I think. No, let's not do it.
Let's go into the I never do that.
Okay.
Right.
But I was wondering, the set backtrace mechanism state is a sort of a global switch, or is it scoped somehow?
No, it's global.
Okay, so like basically at the point where this instruction is run, it is from then on enabled. That's until it somehow suddenly hits a line that says the opposite. Okay.
Yeah. Okay. Yeah, the RTS has basically some state. Now, we'll see in a minute that this actually happens by default normally when you throw an exception. But one reason that you might want to do this yourself is that you might also want to collect backtraces before an exception happens. Right, so we were talking about this running example, right, of writing to a stream that was closed. Now, you might want to know where was that stream closed exception thrown, that's the backtrace. But perhaps you also want to know, well, where was the stream closed in the first place? Right, why is the stream even closed? At the point where we were closing the stream, that was not an exception, right? That was just part of normal operation. The exception happened only when we tried to write to it. But maybe the confusing part is the fact that it's closed at all, right? So you might want to record as part of the closed state of the stream in this example, the backtrace to the call to close, right? That's quite a useful technique that I use quite a bit to figure out where these things are coming from. So that might be one reason why you might want to call this this function called like backtraces, this guy, yourself. All right, so I mentioned just now that actually we get backtraces by default. So let's see that in action. So if I throw, again, my stream close example, and I call this guy now, then I'm seeing the stream close exception with one annotation, which is the backtrace to the call to throw. The reason we were not seeing that before is because in main, I'm actually disabling backtraces for the annotation example here, because I didn't want to get confuse matters by talking about backtraces when we're just talking about annotations, right? So before we were only seeing the sending annotation.
I'm not sure how is the return unit supposed to show me how you're disabling it? No.
Oh, no, it's not. No. So this is so main calls backtrace example with the default settings, not doing anything, then disabling backtraces and then calling annotation example. Right, so before we were
backtraces is explicitly setting all the mechanisms to false.
Exactly. Yeah.
But by default, they're all enabled, or
no? By default, only the call stack
only
one
the call stack one is. Yeah. Mm-hmm.
Yeah.
Okay.
All right. So So if we now annotate this, annotate IO, sorry. Then what we're seeing is we're seeing the exception with our annotation as well as the backtrace annotation. Right, so this is the default behavior. When you throw an exception, you get a backtrace. And so when you run your code with profiling enabled, for every exception that you throw, by default, you will get a call stack to that exception. There is one exception to this rule. Excuse the pun. Suppose that we define some other exception type. And we have the stock again. Now, in this case, I'm going to give a manual instance of exception for some other exception. And why might I want to do that? Well, because I might want to override the backtrace desired option here. And it takes basically a proxy. It's not quite a proxy, but as an argument. So this is irrelevant. It's just like, do you want a backtrace for this kind of exception? Yes or no? Right. And so now when I'm throwing this, and run this again, then I'm not scanning a backtrace. And the reason for this is performance, right? There's a cost to collecting backtraces. So normally, of course, exceptions are exceptional, right? They only happen in exceptional circumstances. So we're not really too worried about the cost of throwing an exception. However, in some cases, that is not always the case. Like some exceptions, like on a timeout or a thread killed or like things like this, right? They are part of the normal control flow of a Haskell program, right? They might happen quite frequently. They're not exceptions. We don't want to debug them. We don't want the additional cost associated with them. So for those things, you can set this backtrace desired to be false if you wish. All right, and that's the new exception story in GHG 9.10. Are there any final questions?
There was like one more question, like sort of like a little bit of confusion which function is actually printing the cost center backtraces. But I mean, I can also try to just retrace. I think it is like, I mean, display backtrace is sort of the, if I understand it correctly, correct me if I'm wrong, is sort of the library given function that you can use at any point, whether you're using exceptions or not. Like if you want a backtrace at some point, you can use display backtraces. And the backtraces you're then getting depend on sort of these globally set flags for which backtrace mechanisms are enabled or not.
Almost, that's almost correct. It's not quite, right? There's a step in the middle. So display backtraces doesn't collect anything. It takes a set of backtraces as argument.
Yeah.
Right.
Yeah,
so
sure.
it's
so you need to first collect them. Yeah. You need to first collect them. The ones that you're collecting depend on the flags that are enabled or not, right? I mean,
Yeah.
otherwise, and then
Yes.
display is just simply
Right.
printing them. Yeah,
Yeah.
exactly.
And so
And
there's,
then, yeah, okay.
sorry, yeah, what were we gonna say?
And then, yeah, I mean, and then the second step was that, like, I mean, you have, that's why we started with annotations, right? That, like, whenever you're having an exception, it now has an implicit annotation that equips it with backtraces automatically.
Yeah, exactly. So the default handler for printing uncaught exceptions in base, right? The function that gets called when your program throws an exception that you're not catching has also been modified to call display backtraces on the backtrace example, on the backtrace annotations if there is one. Right? Like the default exception handler prints all annotations, and the way to print the backtrace annotations is to call display backtraces. Yeah.
Is there any way to use this and remain backwards compatible with older GHCs? Probably not.
I mean, I guess you could define some sort of shim where annotate IO and things like this are defined to be no ops. That would, yeah, that, I don't think that would be too difficult because the types don't change.
Yeah.
Right. So that feels like that should be possible. Yeah.
Okay. Cool.
All right. In that case,
okay. Then thank you for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and feel free to leave any comments either now in the chat. We'll leave it open for 1 or 2 more minutes, or later below the video. And yeah, hope to see you again in a few weeks.